Okay, thank you for joining me in this talk about formation and evolution of terrestrial planets in the 2021 Sagan Summer Workshop. So my name is Izidoro, and I'm a postdoc at Rice University. To get started, let's talk about the first planetary systems that we discovered, the solar system. So planets in the solar system, they come in two flavors. So you have the inner rocky terrestrial planets, and you have the distant giant planets. In the middle of these two groups, we have the asteroid belt. We're going to talk about the asteroid belt later in this talk. But for now, let's focus on the planets. Let's plot the solar system planets in a diagram, orbital period versus mass. That's what we get. So we can now clearly see that giant planets are really giant. So their masses are much larger than the mass of terrestrial planets. And but one thing that's very intriguing about the solar system is that we don't have any planet inside Mercury's orbit. It's intriguing because if you add in this plot all the planets that we have been discovering in the last 20-25 years, that's what we have. So here, the color shows planets that have been discovered by different techniques. And usually, you clump these planets in groups and name them. So planets with masses of between 1 and 20 Earth masses, we call them super Earths or mini Neptunes. Planets close to the star with mass close to that of Jupiter, we call them hot Jupiters. And planets at orbital periods larger than 300 days, we typically call them warm Jupiters. So it's natural to ask, looking at this plot, the question why we don't have something like hot super Earths or hot Jupiters in the solar system. So in this talk, I'm going to use computer simulations to describe the main ingredients of planet formation that might control the formation of these different types of planets, from terrestrial to super Earths to gas giants. So let's first take a look at the stages of planet formation. This is basically our current understanding of how planets form. So we know that planet formation starts in a disk of gas around young stars. So dust grains in these disks, they grow by they coagulate into larger particles that we call pebbles. Pebbles are millimeter or centimeter-sized particles that grow in the disk. So if you look at the dynamics of the disk, of the pebbles and the gas, that's what we have. So anything orbiting on the star is going to feel a central force. So a pebble orbiting the sun, you travel essentially at Keplerian speed. The gas also try to travel around the sun at Keplerian speed. But there's another component in case of the gas pressure force. So the gas velocity around the sun, it is slightly smaller than the Keplerian speed, or sub-Keplerian. That means that pebbles that travel at Keplerian speed is going to feel a headwind and drift inward. This is what we call aerodynamical drift of particles. Aerodynamical drift is something very important for planet formation. So we believe that millimeter and centimeter sized pebbles feel headwind, lose energy, and spiral inwards. They eventually concentrate into clumps, overdense regions, and these overdense regions eventually collapse, forming what we call planetesimals. So planet formation jumps from objects with size of millimeter to centimeter size to something like much larger than something larger than a city, for instance, several kilometers wide. So planetesimals, objects with 10 to 1,000 kilometers, they grow to planetary embryos in two different regimes. They might grow by what we call planetesimal accretion. That's when they accrete and other planetesimals near their orbit. Or they can grow by pebble accretion. That's when these planetesimals grow by accreting smaller particles drifting in the disk, or pebbles. So they grow eventually to planetary embryos. In fact, pebble accretion probably needs some contribution of planetesimal accretion to take over. So pebble accretion is really important to solve one of the long-standing problems of planet formation. So to make a core of the gas giants like Jupiter and Saturn, we have to grow this core to accrete gas before the gas goes away. So trying to do that by planetesimal accretion at larger distance from the star, it's not easy. So pebble accretion can build a core of 10, 20 Earth masses that can accrete gas very easily from the disk in a shorter time scale than planetesimal accretion. So planetary embryos growing by planetesimal accretion stop growing when there is no planetesimals near their feeding zones. But even if there are pebbles near the feeding zone of a planet, it might not grow. And that's because when the planet hits a mass of about 20 to 30 Earth masses, it interacts so strongly with the gas that it changes the gas velocity near its orbit. So here we have a simulation showing this process. So we have a planet sitting right here. So this dark blue region shows one region of the disk where the gas is more depleted. So the planets start to open a very shallow gap. But what's important here is that the gas away from the planet is traveling at sub-Keplerian speed, as I explained before. But the gas that's traveling near the planet, like here, starts to travel at super Keplerian speed. So that means that pebbles that are drifting from the far regions of the planet, they eventually reach this region and stop drifting because the gas now is super Keplerian. So there is no gas drag. So that's what we call pebble isolation mass. So planetesimals, they grow to planetary embryos, as I described before. So if the gas is still around, they might grow to the masses of the ice giants, for instance. And when they reach this mass, they also, as I said before, these large planets interact with the disk. And these interactions leads to angular momentum exchanges, and these planets migrate. If the planet is low mass, like a few Earth masses, or 10 Earth mass, it's migrating the type 1 migration mode. If the planet eventually becomes a gas giant like Jupiter, it most likely open a gap in the disk and migrate in the type 2 regime. After the gas is completely gone in the disk, probably after 5-10 million years, so you might have a phase of giant impacts in the gas-free scenario that might explain the formation of terrestrial planets, for instance. So what we wanted to do in this talk is to use these basic ingredients that I described before to explain, to study the formation of super Earths and terrestrial planets. So let's start with super Earths and look at some statistics of the systems. So super Earths with orbital period shorter than 100 days, they probably orbit at least 30 to 50% of solar type stars. So these super Earths, they come in multi-planet systems, like I showed here in these two illustrations. The TRAPPIST one has 1, 2, 3, 4, 5, 7 planets in a very close to the star with very short orbital periods. If you place the TRAPPIST one planets near the sun, they will be very close to the star, as you can see here in this illustration. So the same is true for the Kepler 11 system. So planets are very close to the star. All Kepler 11 planets are inside Venus orbit. So these planets, they typically have compact orbits, but most of them have no resonant orbits. I'm going to explain what no resonant orbits means later in this talk. So you also believe that the innermost super Earths that we observe are probably rocky. So now I'm going to describe the main setup of the simulations that I'm going to conduct in this talk. So I'm going to start with a disk of gas, so in a disk model. So the disk is hot in the inner parts and cold in the outer parts. So we're going to assume that you have a flow or flux of pebbles in the disk, pebbles in the inner parts. I mean, inside the disk is no line. There's no line is the location of the disk where water condensates as ice. So at temperatures of 170 kelvins. So pebbles inside there's no line, they'll have silicate composition, and pebbles beyond there's no line, they'll be icy, like 50% silicate and 50% water. So as these pebbles drift across different regions of the disk, they sublimate, as we can show here. So silicate pebbles, they are millimeter size, and icy pebbles, they are typically centimeter size objects. So we're going to assume that we have already formed planetesimals in the disk, and this planetesimals has successfully formed planetary embryos. And we're going to start the simulations at this point. So we're going to include the ingredients of migration, inclination, eccentricity damping, pebble accretion in an any-body integrator, and let these planets evolve and grow by accreting planetesimals and mutual collisions to larger planets. We have also gas accretion in some of the simulations, gas accretions onto this course of planets. So here is one of the results that we have. So this simulation starts, as I mentioned before. So we start with a distribution of planetary embryos that we place from 0.7 up to 20 astronomical units. These objects are initially very low mass, so they're about moon mass. So the horizontal axis in both panels shows time. So time goes up to 5 million years. So the top panel shows semi-major axis in the y-axis, and mass is shown in the bottom panel in the y-axis. So let's see what happens with this when these planets evolve. So you're going to assume that in this particular case, so the total mass in pebbles available for these planets to grow, for these planetary embryos to grow, is 190 Earth masses. So these pebbles are drifting by and passing these planets, these planetary embryos. They accrete a fraction of them. And they eventually, at 1 million years, we have some objects that have already like 1 Earth mass. So as these objects grow, they start to migrate inwards, as we can see here by these lines. So at 3 million years, you have planets hitting what we call the disk inner edge. So inside the disk inner edge, there's no gas, essentially. So the planets do not migrate. But they might even enter the inner edge when they are pushed by other planets, as you can see I will show in the next case. So during this migration phase, the planets grow, of course, these planets grow first by pebble accretion up to masses of a few Earth masses, as we can see here. They eventually collide with one another, and they grow even to larger mass, as we can see in this jump of mass right here. So at the end of the simulation, 5 million years. So here is when the gas goes away, and we stop the simulation, 5 million years. So we have at least 6 planets near inside 0.7 EU. 0.7 EU is important because 2.7 EU corresponds to an orbital period of about 200 days. So you can compare this to the Kepler sample, for instance. And the masses of these planets are quite similar to the mass of those planets of the super Earths that I showed before. We have masses in the range of a few Earth masses up to 5 or 6 Earth masses. Now we're going to increase the pebble flux. So you're going to start with an initial distribution of planetary objects that's similar to the one that I use here, but you're just going to double the amount of mass in pebbles available for planet formation, for these planets to grow. And that's what happened. So the evolution is quite different, actually. So we can see that these planets at the end of the gas disk phase, in this case, where the pebble flux is higher by a factor of 2, so there's more mass to planets to grow. So the masses of the final planets are by a factor of 10 larger compared to what we had before. So they also park at near the disk inner edge, as we saw in the previous case, but now they are much more massive. So this pebble flux of about 190 Earth mass of pebbles, it typically leads to the formation of system of super Earths. But if you increase the pebble flux by a factor of 2, then you will get the cores of giant planets. So in this particular simulation, you don't have gas accretion, but I'm going to show in the later in the talk some simulations where you do have gas accretion. Okay, so basically, increasing the pebble flux by a factor of 2 is enough to bifurcate the evolution of the planetary system from building something like super Earth systems or something like giant planets. So now we are going to try to use this simulation that they are successful in producing super Earths to compare how they match observations. Okay, oops. Okay, so we can use to compare the results of simulations and with the Kepler sample, we can use the orbital periods of the planets. Trans observations provide orbital periods. So we can use this to compare the orbital period distribution or the period ratio distribution of the planets that we produce in the simulations with that's observed by Kepler. So if you have more than one planet transiting around one given star, for example, the TRAPPIST-1 system where we have 7 planets, we can calculate the period ratios between adjacent planets. So if this ratio of it's a number like 2 integers, like 3 to 2, it means that these planets are probably near a resonance. What that means? That means that for example, the innermost planet is going 3 times around the star. In the meantime, the second planet is completing 2 orbits. So they are in a synchronous motion. So let's take a look at the final period ratio distribution of the planets in our simulations. So here what we have. So the head curve here shows the cumulative distribution, the period ratio distribution of planets in simulations like this. So we run many simulations like this and plot them together in this head curve. So we can see that at the end of the gas disk phase, these planets, most of these period ratios, you have these peaks, some specific locations corresponds to some first order mean motion resonance, like 4 to 3, 3 to 2, 4, 5 to 6. So what exactly that means? So, okay, let me go back one. Okay, oops. Okay. And just to complete, the gray curve here shows the period ratio distribution of the planets observed by Kepler. So we can clearly see that there is no match at all. So the head curve is completely different from the data observed by Kepler. Just to make sure that this is clear, so the head curve shows that these planets that at the end of the simulation, they have some, they are in resonance configuration, in a resonance chain. And their evolution looks like this. So for example, the 2 innermost planets, they cross like every 3 orbits of the head one at the same location here. So actually this is of course, it's I build these systems to further talk especially. So all these planets, they form a 3 to 2 mean motion resonance. The Kepler sample or the Kepler planets, they have no synchronous motion. The synchronous motion is not like that of the planets. There's no resonant obvious resonant configuration for most of these planetary systems. So that's. So by the way, this is not the full story. So I mean, is the model of that we are building that we cannot explain? No. So you have to further investigate this issue. So now it's in fact what happens. So if you integrate the systems, so remember that I said that simulation stopped at the end of the gas disk phase. But if you integrate that simulation for longer, so the gas goes away and you let the planets evolve dynamically by a few million years or hundreds of million years, that's what happens. So you have two kinds of evolution at the end, not only one as I showed before. So some of the systems, they migrate, so planets migrate inwards, pile up at the disk inner edge, and remain dynamically stable after the gas dispersal at 5 million years. So these systems remain resonance, as I showed before. But some systems, the planets migrate inwards, pile up at the disk inner edge. And after the gas disk dispersal, they become dynamically stable. There is no additional perturbation in the system. They're just naturally unstable. And when they are dynamically stable, what happens is that they break the resonance configuration and they gain, their orbits become more inclined and eccentric. So typically, systems that remain dynamically stable correspond to less than 50% of the simulations. And systems that become dynamically unstable corresponds to more than 85%. So just to make sure, here's another simulation show exactly what's happening in these two different evolutions of the systems. So these planets start to evolve in a very similar way. So they migrate inwards. They grow by pebble accretion. They migrate inwards. They pile up at the disk inner edge. So if you zoom in close into the systems that you're going to see that you have typically a few planets at least very near the disk inner edge. They're in a very synchronous motion. They're in resonant configuration in both cases. But eventually, after the gas dispersal that will happen at 5 million years, so some systems, like the one on blue that shows unstable systems, become naturally unstable. And the red one will remain. Okay, now you can see. So the blue system became dynamically stable, and the planets are more eccentric right now. And the systems on the left remain stable during the whole integration time of the simulation. So this is a stable resonant chain, and this is unstable non-resonant chain. So now let's compare again the distribution of the stable, the head one, and the distribution of the period ratio distribution of the stable systems and the unstable systems in blue. So now we can see that the unstable system, so the period ratio distribution is even more spread than the Kepler data. So what we can do is try to mix a fraction of unstable and stable systems to see if we can match the gray curve. So we use a statistical task to do that, and we find that if you mix about 5% head stable systems plus 95% blue, we get a decent match to the Kepler period ratio distribution. Now, I mentioned before that you have only 5% of the systems that become dynamically stable, that remain dynamically stable. And these systems are, of course, rare, and this is consistent with the Kepler sample. But here I list a few of these systems that form resonant chains that are consistent with the rare stable systems that offer our simulations. So if I have, for example, the Kepler, the TRAPPIST ones, that's one of the most iconic systems. You have also the new TOI 178 that you have 7 planets in a very peculiar resonant configuration. So finally, let's take a look at so you know that this model can match fairly well the orbital configuration of the Kepler sample. But now let's take a look at what this model produced in terms of compositions. So are super Earths rocky, like Earth-like, or what? So we know that from photo evaporation models that most likely the innermost super Earths that have sizes smaller than 1.8 Earths radii, they are most likely rocky. And then this same model suggests that super Earths larger than 1.8 Earths radii have rocky cores with hydrogen and helium atmospheres. But then there is also a debate that from planetary interior models that suggests that super Earths larger than 1.8 Earth radii may be water-rich worlds. So this is still a topic of debate in the community, and you might learn more in the next few years. But there is a more the idea that at least the innermost rock, the innermost super Earths of this that we observe are rocky. It seems something that is probably correct. So the diversity of super Earth's compositions in the simulations that I just showed you. So basically, that depends on exactly where planetesimal formation starts. See, planetesimal formation is more efficient beyond the water snow line. So you usually end up producing super Earths that are water worlds, like this first panel here. So here, each line shows one planetary system coming from one simulation. So the size of the dot scales the mass of the planet. So each dot is a planet, but this is a simulated planet. It's not real. These are not real planets. So in the model B, so we have even like regional mixed compositions. For instance, we can see, let's see this system here. We have 3 planets that have a rocky composition and eventually a white one that you can see from the colors. And then again, we have another planet that has a rocky composition. And the model C, so we can also produce systems that are mostly where the innermost super Earths are rocky, but then you might have in some cases at least some icy super Earths in some locations. So now you have to have better constraints on planetesimal formation to distinguish which model is correct, or even to refute all these models. So okay, so let's then place the solar system in the context of exoplanets. So starting from the question that I raised in the beginning of the talk, so why don't have a super Earth in the solar system? So as I showed before, so with a pebble flux of about 190 Earth masses, so you usually produce super Earth. So here's just a slightly different plot from what I showed before. So here you show the distance from the star versus mass. So here's basically a growth track. So planets, they start with a low mass, like moon mass, and they grow by pebble accretion, migrate, and eventually collide and grow to planets that have masses of about from 1 to up to 10 Earth mass. So this is the flux that I showed before that produce super Earths. Of course, that's what we get here. And this continues marks some collisions that we have also in the other simulations. So we can see here in this case that we have a lot of accretion and also a lot of migration. So the planets start at, let's say, maybe 1 or 2 AU and migrate all the way to close to the star, inside 0.1 AU in some cases. So if you reduce the pebble flux a little bit from 190 Earth masses to 114, that's what we get. The planets grow, but grow a little bit less, as we can see here. Now their masses are between Mars mass and Earth mass, and they migrate also a little bit less. So the innermost one is beyond 0.1 AU. If you reduce the mass, the pebble flux, even more, so it will grow even less. So basically, when you have less mass available in pebbles, so you grow less, of course, but also migrate less because you are smaller. In the solar system, it probably happens something like this. So something have probably controlled the growth of the terrestrial planets. So we know that if you go from this pebble flux down to this, we grow this kind of flux. Oops, let me go back. Okay. So you grow basically, if you reduce the pebble flux, you change the bifurcate the growth from super Earths down to moon mass to Mars mass planetary ambulance. So probably in the solar system, Jupiter was a key in blocking the pebble flux when it reached pebble isolation mass. and starve the inner disk. So that's why the planets growing in the inner disk, the terrestrial planets, could not grow to larger mass to become super Earths. And this, in fact, is consistent with some isotopic data from meteorites and from inner solar system bodies. So here, this plot shows some isotopic systems that we have measured and in the different solar system bodies. So what we can see here is that we have two groups: the head group and the blue group. So these objects, so like for example, Earth, Mars, they are in the same region. So these bodies, these objects in this head region here, they are most likely objects or meteorites that were accreted in the inner solar system. And objects that are in the blue region, they're most likely objects that are accreted in the older solar system. And eventually, so these bodies get mixed later. I'm going to explain in the end of the talk how this happened. But the most likely explanation for the solar system isotopic dichotomy is that Jupiter grew and separate the inner and the outer pebbles. So the material that was inside Jupiter orbits had a different isotopic composition from the material that was beyond Jupiter's orbit. So that means that pebbles that were beyond Jupiter's orbit could not feed the formation of the terrestrial planets. So that means Jupiter probably regulated the pebble flux to the inner system, as I showed in the previous slide. So Jupiter probably formed fast early in the solar system history and prevented pebbles from drifting in. Pebbles that were inside Jupiter's orbit, they were rapidly lost. But of course, they have to first form the planetary ambush to form the terrestrial planets. So eventually, so the solar system might have looked like something like some transition disks that we observe, as we can see here in this illustration. So to conclude this slide, so Jupiter, or maybe even a pressure bump in the disk, prevented the mixes of this, what we call non-carbonaceous and carbonaceous pebbles. So they are pebbles that are in the inner and outer solar system. So it also probably regulated the growth mode of terrestrial planets and prevented, for instance, the terrestrial planets from becoming hot super Earths. In that case, by controlling the pebble flux. So pebbles in the inner disk, they are rapidly lost by drift. And the terrestrial planets in the solar system probably were formed via planetesimal accretion, not pebble accretion. So this is the first reason why maybe the solar system does not have a super Earth. The second reason is that once the pebbles Jupiter forms, Jupiter might have also blocked the formation or the migration of planets beyond its orbit. Like this. And this is a simulation showing this process. So if you, as I showed before, so this is a simulation exactly as those of forming super Earths. But now for simplicity, the simulations are fully formed already, and we assume that they are beyond 5 AU. So there's a disk of gas, and the color shows the mass. So these planets are about 5 Earth masses from the beginning. So the simulation starts. So this planet starts to migrate inwards, as I showed before. So the disk energy is an energy shown here at 0.1 U. So the gas, so the type 1 migrate to the disk inner edge, and they form a resonance configuration there. Then the evolution is similar to what I showed before. Okay. So, but then if the first innermost super Earth, and if the first innermost super Earth becomes Jupiter or a gas giant, then what happens is that it blocks the migration of super Earths beyond its orbit, like this. So the super Earths do not penetrate in the solar system. So, of course, the planets migrate inward right here, as you can see, right? So this is the typical evolution of a type 2 migrating planet. But in the case of the solar system, we have Jupiter and Saturn. And Jupiter and Saturn mass ratio is very special in terms of dynamical evolution that gas disk. And they might have prevented migration when they enter a resonant configuration. So the evolution is similar to what I showed before in the case of a single giant planet, but Jupiter and Saturn stay in place. So then they have collisions. So these planetary embryos that were initially 5 Earth masses, they collide with each other, they grow to about 10, 20 Earth masses, and eventually, so you have a system that looks like the solar system that we have today. So you have Jupiter and Saturn and 2 ice giants. And these 2 ice giants, they were produced by impacts of 5 Earth masses, planetary objects that have masses similar of the super Earths that we observe around those other stars. So maybe Jupiter and Saturn together, they act to block the migration from super Earths from the distant regions of the disk from penetrating into the inner solar system. So to conclude this part, so without Jupiter, maybe the super Earth could be, the Earth could be a super Earth. Okay, let's talk then about giant planets. So we know that reducing the pebble flux, we go from super Earths to terrestrial planetary embryos. But what happens when we increase the pebble flux? Of course, it's probably obvious. Then you grow larger, as I showed before. Okay, yeah. So if you include, if you run simulations with a larger pebble flux, and then we turn on gas accretion to allow these planets to accrete gas and become Jupiters. And that's what we have. So you form a systems of Jupiter-like planets, and then also form some super Earths inside the orbit of the planet. And this is at the end of the gas disk phase. So after the gas disk dispersal, as I showed here, so these systems might naturally become dynamically stable, as I showed before. In that particular case, the dynamical stability is very violent, and the systems of the innermost rocky or super Earths in the systems, they may get ejected during the stability phase. So at the end, we survive only 2 out of these 5 giant planets in very eccentric orbits, as I can show here in this diagram, time versus eccentricity. And 2 planets survive here, as you can see in this top panel. So this evolution is very similar to the one that I'm going to use in this nice simulation by Sean Raymond from 2012. So here, just let's play this again. So the simulations will start at a few giant planets in between 5 and 10 EU, and terrestrial planets start to form inside the innermost planet. But eventually, these planets become dynamically stable because they interact with each other with a disk of planetesimals beyond their orbits. And then this stability is so violent that basically only 2 gas giants survive and no terrestrial planet remain in the disk. So if you have this kind of dynamical stability, as I showed already here for super Earths, we might also even prevent the formation of terrestrial planets. Okay, so this kind of giant planets grow, they become dynamically stable. The dynamical stability is very violent, as we can see, and this is consistent with observations. So this, the right hand panel shows the centricity versus major axis of planets, of gas giants that we observe. What we can see is that most of the gas giants, they have very eccentric orbits. In fact, the median eccentricity of giant planets is about 0.25. Of course, this is far larger than the orbital eccentricity of the solar system gas giants, as you can see here, also plotted in blue. So eccentricity of Jupiter is about 5%. So why is that? Why the solar system is dynamically cold compared to most of the exoplanets that we observe? To understand this process, we have to look at what happens with Jupiter and Saturn in the gas phase. So as I said before, so they migrate, but when they enter in resonance, they might stop migration. They might basically stay where they are. So Jupiter and Saturn migrate inwards. They capture each other in a resonant configuration, probably 2-to-1 or 3-to-2. That means that Jupiter, for instance, go 3 times around the sun. In the meantime, Saturn goes 2, as I showed before. Then you form the ice giants, and they also migrate towards forming a resonant configuration. So you have another resonant chain in the solar system, but now between giant planets. And then what happened? So the solar system, after the gas disk phase of dispersal, you have this resonant configuration. So you have here the terrestrial planet embryos in the inner parts inside Jupiter's orbit. Inside we have also a disk of planetesimals beyond the orbit of Uranus and Neptune that represents the primordial Kuiper belt. So these objects, they're going to interact with these planetesimals, and they eventually become also dynamically unstable. And so this is known as the Nice model instability. But what happened in the solar system that Jupiter is not that eccentric? And so the reason for that is that Jupiter and Saturn, they prevented close encounters. So again, here in head is the distribution of eccentricities of observed planets in a plot from Orbital 2007. And here they plot in the same plot the final eccentricity of Jupiter, one of the Nice model simulations where Jupiter has a close encounter with Saturn. So in that case, the final eccentricity of Jupiter is very high compared to the final eccentricity of the planets that in the order of giant planets in the solar systems. And here is the final eccentricity of Jupiter in simulations or near the current one. Of course, in simulation, if there is no close encounters. Of course, so some Nice model instabilities do not produce the solar system. Some produce something completely different. So why we don't have Jupiter and Saturn in very eccentric orbits, or maybe at least Jupiter in a very eccentric orbit, since once Jupiter and Saturn have a close encounter, so the most likely outcome is to get Saturn ejected. So the reason for that is that they avoid close encounters during the instability. Okay, so now let's talk about the formation of the solar system and why we get these beautiful terrestrial planets. So let's take a look now finally at the asteroid belt. The asteroid belt is complicated. So the asteroid belt has a distribution of objects that has very high eccentricities and inclinations. So that's very different from the planets. So asteroids that show here in this dot, these white dots, they have inclinations, eccentricity from 0 to about 0.3. So they're very eccentric. And they have inclinations from about 0 to up to 25, 30 degrees. They're very inclined. So the total mass in the asteroid belt is very low. It's about only 10 to minus 3 Earth mass. You see, this is the largest body of the asteroid belt. So in terms of solar system constraints, we have also Mars. Mars is very peculiar because Mars has a very low mass. And we also know that the Earth is not dry. So you have to explain these constraints if you wanted to produce a model for this inner solar system. So take a closer look at the asteroid belt. So we know that the inner part of the asteroid belt is dominated by what we call S-type asteroids. That means asteroids that are water, essentially waterproof. But the outer part of the asteroid belt is dominated by water-rich asteroids. So I mentioned before the solar system's isotopic dichotomy. So the head population, that plot that I showed before, is essentially corresponds to the non-carbonaceous meteorites, basically sample S-type asteroids somehow, in for simplicity. And the CC carbonaceous meteorites basically sample the population in the older parts of the asteroid belt. Okay, so finally, solar system formation models. So let's take a look at the classical scenario. So the classical scenario starts with a distribution of planetary embryos, so inside Jupiter's orbit. So for simplicity, these models typically assume that there is no gas in the disk anymore. So the Jupiter and Saturn are fully formed. And this population of objects, they're gonna to interact with each other if the giant planets, if they star and collide and grow into form a system of terrestrial planets. So the color here shows the amount of water in these objects. That's typically, we assume that bodies inside the 1AU are dry and bodies beyond 2AU have some water. Based on the current meteorite content. So eventually, the system evolved, and in the end, you go from populations of several Moon to Mars mass planetary embryos to 3 final planets. So you can see here that the systems is basically probably a terrible match to the solar system. And this is intentional, of course. So here you have the most massive planet. It's inside. It's about 0.6 AU, 0.8. So the Earth is smaller than Mars, the planet that's here. We have no Mercury. That's challenging many simulations of the classical scenario, and still today. And what we can see here is that the colors of the planets are, of course, they will find a water content. They have a lot of water, but that's not the main issue. The main issue in this kind of simulations is the mass of the planet that's forming around 1.5 EU. And in this case, as you can clearly see, it's larger than the mass of the planet near 1 EU. If you run many simulations like this, what's going to happen is that you going to have a result like that. So the square shows the real terrestrial planets, and the circle shows the simulated planets. So we can clearly see that most planets that are forming around 1.5 AU, where you should get in Mars, they are typically much larger, at least 5 times larger or a few times larger than Mars. So that's what we know as small Mars problem. And this problem has been around for more than, since actually 1991. So in 2009, Brad Hansen proposed this very elegant solution that we are using basically wrong initial conditions. We should not start with a disk that's very wide like this, but with something like that. If you run many simulations using a disk that's that narrow, I mean, starting with a distribution of planetary objects from 0.7 up to 1 AU only, that's what we get. So here again, this the filled circles are the real planets, and the open ones are the simulated planets. But now we can clearly see that we can produce Earth analogs, Venus analogs, sorry, and of course Mars analogs. That's what matters. Okay, but then the simulations cannot explain how we get the asteroid belt. Okay, but it gives us teach us a very important lesson. It shows that to produce Mars, you have to have a very severe mass deficit from 1.5 to 4 AU, about. So now we have 2 different solutions to explain this inner solar system. The first solution is that the belt was born massive as in the classical model, with a lot of water and later depleted. And here is this idea. So we start with a high mass belt, and then we bring Jupiter too close to the star, and then we truncate the disk in the Hansen style way. And this is known as the Grand Tack model. So here's a simulation of the Grand Tack model showing how this process works. So we assume that so each snapshot here is a motion at a different time, of course. So Jupiter is here fully formed. Jupiter starts to migrate inwards. And then Saturn is still growing. Saturn migrates faster because it migrates in a different regime. And it catches up with Jupiter in resonance. And then this, in some cases, they might reverse migration. It's indeed seen in simulations. I'm going to discuss this in the following slide. So they truncate the disk and they migrate back. So when Jupiter and Saturn migrating, they deplete the belt, creates a Hansen style disk. And when they migrate back, they repopulate the belt with a mix of asteroids coming from different locations, like water poor and water rich objects, as we can see in the final snapshot here. The end of the simulations of 100 million years, we can get 4 terrestrial planets, and Mars is as small as it should be, as we can see here. So in the Grand Tack model, we also deliver water during the outward migration of the giant planets. And the Grand Tack model is also broadly consistent with the orbital structure of the asteroid belt. So the Grand Tack model invokes, as I said before, just sorry, invokes one specific migration history of the giant planets. And here we show some plot showing that the migration of the Jupiter and Saturn in the disk is extremely sensible to the disk structure. So some disk models might lead to migrations like the Grand Tack needs, but some disk models might lead to inward migration, or the planets are capturing resonance and stop migrating, or even continue migrating inwards. So we don't know yet if the migration of the Grand Tack, for instance, is possible to be achieved when the planets are realistically accreting gas from the disk. And then we have also another model that's called the early instability model. The early stability model also assumes that the belt was born high mass as the classical scenario. So the inner parts of the disk has about 2 Earth masses of material. We have at least 2-3 Earth masses of material in the asteroid belt, and a lot of mass, the giant planet region, to make the giant planets. And this model invokes giant planet instability, exactly as I discussed before, to deplete the asteroid belt and to make Mars small. So here's a simulation of this process. Here we have Jupiter and Saturn and 3 giant planets, 3 ice giants. So these extra giant planets is invoked in the simulations because it's typically ejected during the evolution of the system. And this has proven to be very successful in explaining several characteristics of the solar system. So let's play the simulation. So these planets start to evolve, and eventually they become dynamically stable, as I showed before. So Jupiter and Saturn, they reach their current orbits, but this dynamical evolution of the giant planets deplete the asteroid belt at some level that might be consistent with the current belt that we have today. Finally, we have also the low mass asteroid belt that assumed that the belt was born low mass from the beginning. So we have at least 2 Earth masses of material around 1 AU, a very low mass, probably some amount of mass comparable to the current mass in the belt today. And you have also a lot of material available to make the giant planets beyond a few AU. The problem with this scenario is that it can match the mass distribution of the planets, as we can see here. So here's the results of many simulations plotted together. So the circles again shows the simulated planets, the triangles shows the real planets. The belt from this simulation is very low mass. So as you can see, because the belt is very low mass, Mars is naturally small. It can even produce some Earth and Venus and even a few Mercury's analogs in terms of mass, at least. But if you look at distribution of the objects in the asteroid belt, remember the Grand Tack, leaves the asteroid belt in a dynamical state that's consistent with current configuration. The early stability model probably also do that. But here in the low mass asteroid belt model, the dynamical excitation of the asteroids in the belt is too low, as you can see. So the box shows the region corresponds to the distribution of the eccentricity of the asteroids. So you should fill the entire box essentially to match the asteroid belt. And you can clearly see that the population of asteroids beyond 2.5 AU are under-excited. So there's no match, both in terms of eccentricity and inclination. But then there's a missing ingredient in this scenario. That's the orbital chaos. So that we call it simply the butterfly effect. So Jupiter and Saturn, also during the instability, they might excite the asteroid's orbits, not only depleted as in the early stability model, but also excited, even if the belt is below mass. And so here's a simulation showing this process. So the asteroid are these black dots. So you have a plotting same major axis versus eccentricity and inclination. So asteroids are initially dynamically cold, as we can see. Eccentricity is set 0 and inclination also very small. And you place Jupiter and Saturn in a kind of dynamical instability evolution near their current orbits. and they let them evolve with this population. And you can see that if the orbits become dynamically chaotic eventually during the evolution, they excite the asteroid orbits. As we can see here, this simulation. So the asteroids orbits are excited up to very high levels, and the inclination as well. So the evolution of the giant planets in these simulations that can excite the belt is fairly consistent with other solar system constraints, but there is no, we have no idea how the asteroid belt should be low mass yet. So where did Earth's water come from in these new scenarios of planet formation? So here you have, again, Earth is not dry. We have the asteroid belt, so Earth, Mars. Asteroid belt is dominated by S types in the part and C types in the other parts. But this is what happens to deliver water in this scenario where there is no outward migration of Jupiter and Saturn in the disk. So here's a simulation show what happens when Jupiter and Saturn grows in the disk of gas. So here we have a distribution of planetesimals coded according to their initial locations. And we have here the cores of Jupiter and Saturn. Sorry. These cores, they grow by accreting gas. But there's no migration included in this case. So that's what happened. The simulation starts. The population of planetesimals starts to interact with the cores. The cores are small, but when the cores start to grow, so Jupiter starts to scatter and asteroids everywhere, and the gas drag acts to dump asteroids in the asteroid belt. As we can see here, this is kind of raining into the asteroid belt. And Jupiter and Saturn grows, it reduces the process. It also scatters a lot of material from beyond its orbit into the asteroid belt. So, so these objects that have very eccentric orbits, they might deliver water to the Earth because they're going to cross the orbits of the growing terrestrial planets. And also, this explains how we can get the C-type asteroids in the asteroid belt today. So the source region of material that's implanted in the asteroid belt and deliver water to Earth is very wide, at least 5 4 AU wide in this particular scenario. But the point of this is that this process is very generic. So whenever a giant planet grows and there's planetesimals nearby, it's going to scatter. And if it's, it might scatter material into the inner system and deliver the water to the terrestrial planets. So the Grand Tack, of course, also deliver water to the terrestrial planets and explain the mix of S and C-type asteroids in the belt. But the point is, there's no need of outward migration to pollute the inner solar system with water-rich bodies. Just to summarize, so we have today these different views of solar system formation. We have the Grand Tack model. The Grand Tack model proposed that Jupiter migrates inwards, truncate the disk. Then Saturn migrates in. So they scatter population of S types beyond their orbits. They migrate back to their current orbit, near the current orbits. And you have an asteroid belt that's dynamically excited, and you can make Mars small. The low mass asteroid belt assumes that the asteroid belt is born low mass from the beginning. Then Jupiter grows, scatters planetesimal C-type planetesimals in the asteroid belt. Saturn does the same. They eventually become dynamically stable or chaotic, and they excite the asteroid orbits. And Mars is also small because there's no mass in the belt from the beginning. Not a lot of mass, at least. So the early stability model assumed that the belt was born very high mass. So Jupiter grows, scattered C-types inward. Saturn grows, does the same. And they together become very violent and deplete the asteroid belt orbits. The asteroid belt making possible to make a low mass Mars. So these are the 3 views of solar system formation. And I'm gonna stop here. And thank you for watching.